Hello everyone, this is Professor DePaulo welcoming you back to Site 220 Behavioral Statistics fully online. And this week we're going to be talking about the t-test for two independent samples, which is a logical extension of what we did previously, which was the t-test for one sample. So some of the learning outcomes for this chapter include understanding the structure of the research study. So when is it appropriate to use an independent measures t-test? So independent measures t-test is also known as a between subjects t-test, when you have independent people or different people in two groups. So t-test always means two groups. Independent means those two groups are not related. There's different people in group one versus group two. And then later we'll be talking about repeated measures t-test where you have the same individuals in group one and group two. It's like a before and after. That's going to be the next chapter. We'll be talking about the test the difference between the populations, two population means. So basically, one mean represents one population, the second mean represents a population after the treatment was introduced, and is there a significant difference between those two? And then evaluate, if there is a significant difference, especially evaluate how meaningful the difference is by calculating effect size. And effect size is calculated using either Cohen's d or r squared. And sometimes people will calculate confidence interval to say that we're 95% confident that the true population difference is between these two boundary points. But really, the main versions of effect size are Cohen's d and r squared. And then understanding the assumptions of these tests and whether you need to adjust the calculations if possible, and that's best done with a computer. So most of the research studies that we do as psychologists involve two or more sets of data. So you have two groups, generally. One group is the control group. That group gets nothing. And the other group is the treatment group, and they get the treatment. And then we compare the control group to the treatment group to see if there's a difference. We hope that the treatment group is superior in some way to the control group, because the control group represents the null hypothesis, and if there's an effect, that represents the alternative hypothesis. That supports the alternative hypothesis. If these groups are completely different people in each group, they're called between subject design or independent groups. And that's where you get the independent groups t-test. You may hear it referred to as between subjects t-test as well. If the groups are related, like the same people in both groups, then you get to what is called the within subject design or repeated measures design. So that's in chapter 11. Chapter 10 deals with just the independent groups design or the between subjects design, which is probably the most common type of two-group experiment you're going to run. Computational procedures are a bit different depending on the design you're using. The independent groups design is going to be different than the single sample design, because now we're not comparing one sample to a mean, an established parameter, some kind of value. We're comparing these two samples together, and each sample represents a different population. There are strengths and there are weaknesses of the between subject design. It is a very common design, and I think the strength is that you can really show a manipulation having an effect. So you can really show that the treatment works. With a two-group design, you can't do that with a single group design. Basically, in psychology, a single group design is only if you're comparing a sample to an established parameter, which is pretty rare. Most of our research studies are either going to be independent groups or between groups, or the repeated measures or the within groups design. And between group design allows us to avoid some of the pitfalls of the repeated measure design. And the biggest pitfall of the repeated measure design is that the groups are not independent, and so they may influence each other. When you have independent groups, you have different people in each condition, there's no potential ability for there to be kind of an interference effect, right? So you don't have to worry about, people in one group affecting the second group. If you're doing a within subject design, which we're going to be doing later in the course, you do have to worry about, group one versus time two, that there's some kind of contamination. So with the between group design, you have a control group and then you have a treatment group in general, right? And so the control group, the sample that gets nothing, or the control group, they represent one population. The sample that gets a treatment represents a different population, you would hope, right? So the idea is that treatment is superior to the control, and so they come from two different populations. That's the supporting the alternative hypothesis, the research hypothesis. If you don't support the research hypothesis, then you can say that the two samples come from the same population. That population represents the null hypothesis, where basically there's no effect of the treatment, right? So if the two samples are not statistically different, then they basically come from the same population where the treatment has no effect, or the treatment hasn't been introduced. And we want to avoid that as researchers. We want to say that this sample really does not belong with the null hypothesis population. It belongs to some alternative population, which is better than that null hypothesis scenario. So some of the hypotheses for this design, the null hypothesis represents no difference. So the two populations, there's no difference between them. In essence, they're the same, right? There's no difference in the means of those two populations. So even though we're testing two samples, they come from the same population. That's the null hypothesis, that these two samples come from the same population. They're random samples from the same population where the treatment doesn't work. So whatever your idea was, whatever your hypothesis is, it doesn't work. And these are just two random samples from that population. The alternative hypothesis is that they're not the same, that these two samples represent two distinct populations. And therefore, they're not equal to each other. Another way of writing that is mu1 minus mu2 does not equal 0. That means they're not the same. And it's easier to write it like this because when we test the hypothesis, we're testing the hypothesis of the mean difference between those samples. And we expect the mean difference under the null hypothesis, the mean difference is 0. Under the alternative hypothesis, the mean difference is not 0. This is obviously two-tailed, or non-directional. So we're just saying that there's some difference between these two groups. They don't represent the same population. Now, when we plug it into the t statistic, it gets a little more complicated, but it's not that complicated because that second term, if you look at the numerator here, mean 1, sample mean 1, minus sample mean 2, minus this difference of population means. So that represents the null hypothesis. So under the null hypothesis, that second term in the numerator, where you see mu1 minus mu2, that second term is 0. So you can cross out that second term because we're always testing this against 0 because the null hypothesis says there's no difference. So therefore, mu1 minus mu2 will be the same, so it'll be 0. So if you cancel out that second term and make it 0, then all you're left with in the numerator is mean 1 minus mean 2. So it's mean 1 minus mean 2 in the numerator divided by the standard error of the difference between the sample means in the denominator. We'll talk about how to calculate this. So just eliminate that second term because that second term is 0. And then the numerator will become mean 1 minus mean 2. You can cross out the mu1 minus mu2. The second term, cross that out. That's 0 for basically our purposes. Now, if you want to calculate the denominator of the t statistic here, we need to have the basically standard error of the sampling distribution of the differences between means. That sounds like a whole bunch of jargon. But basically, what this is saying is this is what would happen if the null hypothesis is true. This is the average, basically, discrepancy. So if you took two samples at random and you found their difference, and you did that over and over again, you took two samples at random and you calculated the difference between the two, and then you plotted it, and you did it again, and you did it again, and you kept doing it, you'd have some variability there. You'd have a distribution. That distribution would be the difference between the sample means. The standard deviation of that distribution of the difference between the sample means would be known as the standard error of the difference between sample means. And it's given here at the bottom, and it's equivalent to the square root of the variance of sample 1 divided by the sample size of sample 1, plus the variance of sample 2 divided by the sample size of sample 2. So that's the standard error. That's basically the standard deviation if you were to plot all possible differences between sample means. So if you took two samples at a time, found their means, and then plotted the difference between those means, and you did that as many times as possible from your populations, right? And you plotted those differences between the means, you'd have a distribution. The standard deviation of that distribution would be what you're seeing on the bottom of the screen here. It would be the standard error of the sampling distribution of differences between sample means. It doesn't matter what it's called, it's jargonish. All you need to know is that this is the average difference between the difference between sample means taken over and over and over again. And this goes in the denominator of the t-statistic. Now, if the sample size is not equal for your two samples that you're taking, in order to calculate the standard error, or first you have to calculate the variance, you're going to have a discrepancy here. So the pooled variance is basically a weighted average of the variances, and it gives more weight to the sample that has a larger sample size. If you have equal sample sizes, if n1 equals n2, you just have to basically average out the two variances, and that would give you the pooled variance, just to find the direct average. So variance of group 1 was 10, and the variance of group 2 was 6, and you had the same sample size, it would be 10 plus 6 over 2, which would be 8. But a lot of times we don't have equal sample sizes, and the fraction that you're seeing on the screen will help you calculate the pooled variance, especially if you don't have equal sample sizes. Now, I suggest using this for everything, equal or unequal, because it works for everything. And it's a very easy fraction to solve. So the pooled variance estimate equals the sum of squares of group 1, sample 1, plus the sum of squares of sample 2, divided by the degrees of freedom of sample 1 plus the degrees of freedom of sample 2. And if you do that, you'll be all good. Now, if you have variances instead of sum of squares, you can go from variance to sum of square by just multiplying by n. So if you multiply the variance by the sum of squares, if you multiply the variance by the sample size, you're going to get the sum of squares. And if you take the sum of squares and divide by sample size, you're going to get the variance. So all you have to do is multiply the variance by the sample size, and you'll get the sum of squares, if for whatever reason you don't have the sum of squares to begin with. Now, once you calculate the pooled variance, the s squared sub p, you can find the standard error of that t-statistic that you need, right? The standard error of the difference between sample means. And it's written as, you see, s sub m1 minus m2. So it's the standard error of the difference between the sample means. It's equal to the square root of the pooled variance divided by N1, the sample size of group 1, plus the pooled variance divided by the sample size of group 2. So all you do is once you find the pooled variance that you did in the last slide, you plug it in, divide by the sample sizes, and take the square root, and that gives you the denominator. That gives you the standard error for your t-statistic. So it's not a very difficult calculation. You also need the degrees of freedom because that's in the denominator of the pooled variance estimate. The degrees of freedom are equal to n minus 1 for group 1 plus n2 minus 1 for group 2. So it's basically n minus 1 for both groups, which then gives you a total of n1 plus n2 minus 2 overall. So if you take the 1 degree of freedom out from the first sample and you take the 1 degree of freedom out from the second sample, you'll end up with n1 plus n2 minus 2 as your total degrees of freedom. But you'll need that for the pooled variance estimate. And you also need the total degrees of freedom when you find the critical values of t in the table. You'll need the total degrees of freedom. So let's look at a review question here. Which combination of factors is most likely to produce a significant value for an independent measure's t-statistic? So how would you get a significant t-value? That means basically how would you get a larger t-value? Well, the t-statistic is the variance, right, divided by the sample size, the square root of the sample size, that's the denominator. And in the numerator, you have the mean differences. So the bigger the numerator, in order to get a big numerator, you have to have a large difference between the two means. So that would give you a larger t-value if you had a large difference between the two means. Also, if the denominator is smaller, you're going to have a bigger t-value. So how do I get a smaller denominator? Well, have a smaller variance. So if the variance is smaller, the denominator will be smaller, and therefore the t-value will be bigger. And also, if the sample size is large, the denominator will be small, and that will also give you a bigger t-value. So there's a couple ways to increase the size of the t-statistic. One is make sure the mean difference is big. You know, the difference between the two groups, the mean difference, make sure that's as large as possible. That's one way. The second way is make sure your variance is small. And the third way is make sure your sample sizes are large. Probably the easiest way to increase the t-value is just increase the sample size. It's hard to increase the difference between the two means because that's more related to the size of the effect, and you don't really control that. The variance, once again, it's hard to control that. The easiest way to control the t-value is sample size. So if you increase sample size, you're going to increase t, you're going to be able to reject the null hypothesis. So for the answer for this, it's going to be a large mean difference and a small sample variance. And that's the answer. Large mean difference, so the numerator is large, large mean difference, and a small sample variance. And obviously, you know, if you had an option here, you'd go for the large sample size. So let's review these two true-false questions. The first question, if both samples have a sample size of 10, the independent measure's t-statistic will have a degrees of freedom of 19. Well, the formula for degrees of freedom is n1 plus n2 minus 2. So 10 plus 10 minus 2 does not give me 19. And for the second question, for an independent measure t-statistic, the estimated standard error measures how much difference is reasonable to expect between the sample means if there is no treatment effect. And that's basically what it does, right? So that's the standard error of the difference between sample means is the average difference between two means taken at random, you know, from two samples, taken at random from a population where the null hypothesis is true. So there's no effect, right? So it's just basically error variance, random error. And that's what we have here is random error. So every time you take two samples, even if the population means are the same, right? There's no difference. If you take two samples, you're going to have slight differences. Most of those differences will be near zero, but some of the differences will be more extreme, and that's due to chance. So that's what the standard error of the difference of means is. It's like basically the average difference between two samples taken at random from a population when the null hypothesis is true and there's really no difference between the means uh, of those populations. And so this is what we have with degrees of freedom. The degrees of freedom is actually 18. And the statement about the standard error of the difference between sample means is accurate. It's always under the situation where the null hypothesis is true, that there is no difference in the population. So how do we run hypothesis tests for these independent groups t-tests? We first state the hypothesis. Well, we have two hypotheses. We have a null hypothesis that says no difference. There's no effect in the independent variable. And we have an alternative or research hypothesis that says that there is a difference. And it could either be non-directional, or you don't indicate the direction of the effect, or it can be directional, or you indicate whether it's greater than or less than. You then locate the critical region in the table. So if you find the degrees of freedom, which once again are n1 plus n2 minus 2, you find those total degrees of freedom. You look it up in the table. You have to look up the alpha value, whether you're testing at a 0.05 level or something other than that. You got to look up whether it's one-tailed or two-tailed, directional or non-directional. And then you have the critical value. You then collect the data, you compute the test statistic, you compare it to the critical value, and you make a decision. If your obtained value is more extreme than your critical value, you reject the null. If your obtained value is not as extreme, it's more towards the center of the distribution compared to the critical value, then you fail to reject the null. You should only use directional if you are almost guaranteed to know the difference of the direction of the effect. And even then, I would say it's probably not a good idea. In research, it's almost never a good idea to use directional hypotheses. One, you might make a mistake and you might have an effect in the opposite end. So you might be thinking increase, increase, and then there's a huge decrease. If you're using a directional to look for an increase, you're never going to find the decrease if it shows up. So sometimes we don't know exactly what's going to happen, and we get huge results in the opposite direction of what we think is going to happen, and we can't find those big results, accidental results, when we use a directional test. So you really try not to use directional tests as much as possible. And it's just not good practice in terms of publications. People get on you about using one-tailed tests, directional tests. You need to, if you're going to use a directional test, you need to verify, you need to justify why you're doing it, and it has to be obvious. And if it's not obvious and justifiable, don't do it. Now, the benefits of using the directional test is it has more power, so it's easier to reject the null hypothesis. And I think that's the benefit of why people try to use it. It's just that if you're not 100% sure of the effect, and you can't make an overwhelmingly consistent, convincing account of why you're doing it, then just stick with two-tailed or non-directional. Here's an example of the critical values. So this is for degrees of freedom of 14 at an alpha value of 0.05. So this is a non-directional or two-tailed test. And you can see the two critical values plus 2.145 and minus 2.145. And if you compare this to Z, remember with a non-directional Z, we had 1.96 and negative 1.96. This is more putative than Z. So these critical values are higher than the corresponding Z critical values. And so it makes it harder to reject the null using t here. Now, if the sample size gets bigger, right now our sample size here is 16. If the sample size was larger, then the t critical values would be smaller and they'd be closer to the what you'd have with the z critical values. And at infinity, they'd be exactly the same. So at infinity, sample size, t and z are the same. But if you have 30 or more, you're going to have very little discrepancy between t and z. But here we don't. We have 16, so you see that the critical values are a little more punitive. Now your obtained value has to be more extreme than these two critical values. So it has to be either greater than 2.145 or less than negative 2.145. You need it more extreme than the critical value to then reject the null hypothesis. Some of the other assumptions for the independent groups test, independent measures test, and these are not overly stringent. That means you can violate these to a degree and still be okay. Observations with each sample must be independent. So with the independent group design, you should have independent individuals, different people in each group. And if you have different people in each group, they're going to be independent of each other. They're not going to be related. That's if the sample is drawn at random. So you want to draw the sample at random if possible from the population. Make sure that every member of the population has an equal chance of being selected. That's the best way to do this sampling. If you don't do it, then make sure, if you're using a convenient sample, make sure that the individuals in each group are different. So they're independent. The two populations must be normal. This is guaranteed under the central limit theorem. So if you have 30 or more people in each sample, you are guaranteed a normal sampling distribution. So that's not a problem. If you have less than 30, then you want to make sure that the samples are drawn from are normal. And would you know that or not? I don't know. You might not know that. So you might have to take a chance, right? But what the good thing about these assumptions is they don't really hurt you that much. So if you don't meet them properly, you may be penalized a bit. But if your parent distribution is not completely normal, it's normal-ish, you'll be fine. The only time you would have a problem with the normality assumption is if you had a very small sample size, under 30, and the populations where the samples are drawn from were extremely skewed. Then you'd have an issue. But that's not the case. So it's very easy to get 30 people in a sample. So do it. They don't have to worry about this. And the two populations must have an equal variance. This is called the homogeneity of variance assumption. If they don't have equal variances, that's a problem. Now, the good thing about this is the variances could be off a bit. They can be different quite a bit, and they'll still be okay. The rule of thumb that I use is that the largest variance should be no more than 4 times the smallest. If your largest variance is more than 4 times the smallest, you have a problem with the homogeneity of variance assumption. You'll have what's called heterogeneity of variance, which means that you can't run the t-test. Or if you do run the t-test, you get penalized and you have to use a different value for the degrees of freedom. But if the largest variance is no more than 4 times the smallest, you're generally okay. Now there's a couple of tests that the book talks about in terms of testing this homogeneity of variance assumption, and I'm going to go through the tests. But generally the rule of thumb is if the largest variance is no more than 4 times the smallest, you're okay. One way to test this homogeneity of variance more formally than the rule of thumb I gave you is to use the Hartley F-max test. And it kind of does the same thing. You take the largest variance in the numerator and the smallest in the denominator, and you want to have that fraction to be less than 3 or 4, because that will basically guarantee that your homogeneity of variance assumption is fine. So the largest variance divided by the smallest variance, you should have a value close to 1. If your value is close to 1, you're good. If your value is 3 or 4, 3 is a little bit tricky. 4 is definitely really tricky. 4 is where you're going to kind of push the boundaries for violating the homogeneity of variance assumption. And if you violate it, then you can't run the t-test. And you got to use a non-parametric test, which we will not talk about in this class. But you want this ratio close to 1. So here you don't want to reject the null hypothesis. The null hypothesis says that the variances are the same. You don't want to reject that null hypothesis. So this is one instance where you don't want to reject the null. One of the few instances. The alternative is that the variances are different. You want to make sure that the variances are the same. So you don't want to reject the null for this test. And there's a chart in your text that gives you the critical values for testing this ratio, the Fmax table. Now to measure the effect size, we can estimate it using Cohen's d. Cohen's d is the estimated mean difference, so mean 1 minus mean 2, divided by the estimated standard deviation, which is the square root of the pooled variance, square root of s squared sub p. So if you calculate the pooled variance and you take the square root of it, you have the denominator, and the numerator is the same thing you have in the t-test, mean 1 minus mean 2. As you can see here, there's no reference to sample size. So effect size always is the importance of the effect of the independent variable without relying on the sample size. You can also calculate effect size using R squared, which is the percentage of variance explained in the data set. And this is calculated by squaring the t statistic in the numerator and doing the same thing in the denominator, square the t statistic and then add the degrees of freedom. And the bigger this value is, the better your independent variable is affecting, right, is having an effect, right? The stronger the effect you're having with your independent variable here. So you want large Cohen's d's and you want large R squared values. R squared is basically the ceiling of R squared is 1. So you can't get above 1 here for the R squared. So it's between 0 and 1. You want something, the larger the better, right? But you can't go over 1. With Cohen's d, you can go over 1. And if you're over 1, you have a huge effect. So that's a great thing. You'd rather be over 1. Or rather be as high as possible again. Now, if you wanted to form the confidence interval for this independent groups T design, you would need to put it into this format. Mean 1 minus mean 2, so that's sample mean 1 minus sample mean 2, plus or minus the t-value. The t-value you would get for the confidence interval, if it's say like a 95% confidence interval, you would look up 0.05 two-tailed in the table, and that would get you your critical value there, with the appropriate degrees of freedom, of course. If it's a 90% confidence interval, you would look up 0.10 two-tailed in the same table. So whatever the confidence interval is, you're just subtracting it from 1 and then looking up that value two-tailed in the table. And then S is just simply the standard error. So that's just the square root of the pooled variance that we showed before. And if you add or subtract these values, you'll have a lower boundary and an upper boundary. It's a pretty basic calculation. So the confidence interval gives you an indication of the size of the treatment effect. And this can tell you whether or not you're going to get a significant result. So if the confidence interval contains 0, you do not have a significant effect. If the confidence interval does not contain 0, then the treatment worked and you have a significant effect. So that's the goal of the confidence intervals, is you don't want that confidence interval to contain 0. If it's outside of 0, you're good. That means your treatment worked. If it contains 0, then you can't reject the null. So it's an alternative way of testing a hypothesis, basically. And here's what I mean by containing zero. Let's say your confidence interval is 0.782 all the way till 7.218. That's your 95% confidence interval. That means you're 95% confident that the true population difference, right, the difference between the population 1 and population 2, 95% confident that it falls, that true population difference falls between these 2 points. And as a researcher, that's a good thing because you see that 0 is not in this interval. This interval is 0.782 all the way to 7.218. There's no 0 there. So that means that the treatment most likely has an effect, right? It's not 0. And based on this, since 0 is not in this interval, you can reject the null hypothesis. So since 0 is not in this interval, you can reject the null hypothesis. If 0 was in the interval, the confidence interval, then you could not reject the null hypothesis. You would fail to reject it. So it's a backwards way of basically testing a hypothesis. Now, if you're reporting the t-value in a research article, you need to report whether the means of the 2 groups are different, significantly different or not. And if they are, you've got to report the t-statistic, and you've got to report the p-value, the probability value. And you hope that's less than 0.05 because that's generally the level of significance, right? Your alpha value. You should also give the means and standard deviations for each of the 2 groups. And when you report the t-value, you're going to report it with the degrees of freedom in parentheses. So it's going to be t, and then degrees of freedom in parentheses equals whatever you got. And then reporting the actual p-value, the probability of a type 1 error, which you hope is less than 0.05. That means it's significant. Then if you wanted to report the confidence interval, you could put the confidence interval in brackets at the end if you wanted to do that. Once again, you want to have small variances and large samples. So if we go back to what we want in terms of getting a large t-value, we want a large difference between the 2 means. So the numerator is a large difference between the 2 means. We want a small variance, pooled variance, and we want a large sample size. That's going to maximize our t-values. And the easiest way to control that is the sample size. So jack up the sample size, and you're going to get a bigger t-value, and you're going to say that there's a significant difference. And that's what you want to do. Now, that doesn't mean that the effect is really major. The effect you have to measure with effect size. But to have something be statistically significant means that it's real. There's a real difference there. And that's something you can report and publish. Even without the huge effect size, you can report and publish a significant effect. However, if your sample size is thousands and thousands of people or objects or whatever, then you're really going to have to report the sample size because people get very suspicious when your samples are abnormally inflated, like thousands of people. You know, the researchers are going to say, well, is this really even something meaningful? You have thousands of people in this sample, and they're going to want to see the effect size. And if your effect size is really small, you can report it, and it's going to decrease the value of your research. So hopefully you have a significant result and a large effect size. That's what you want as a researcher. Significant result and a large effect size. And the one way to get the significant result is boost the sample size. One way to increase the effect size is reduce the variability and increase the potency of the treatment effect. That's kind of hard to do, but those are 2 things that can boost the effect size. Let's look at another slide here. For an independent measures research study, the value of Cohen's d or r-squareds helps to describe what? Well, it has nothing to do with type 1 or type 2 error. That's, p-value, right? That's sample size. Would have a lot to do with that. Cohen's d talks about the effect size, so the difference between the treatment the two samples in terms of the treatment and the variabilities in the denominator, right? So it's basically how much difference is there between the two treatments. That's what Cohen's d or R squared talks about. How, what's the size of the effect? How much difference is between the two treatments? And it gives you a quantifiable measure. The last slide is on true false. The homogeneity of variance assumption requires the two sample variances to be equal. Well, they're not going to be equal. They're going to be a little bit different. You want them to be similar. But what we're really testing is the population variances. We're using the samples to make an inference about the population variances. And we want the population variances to be equal. The two sample variances should be relatively equal, but they're not going to be exactly the same. That's why you had that Hartley F max test. You don't want the largest one to be more than 4 times the smallest. And if the researcher reports that T of 6 is 1.98, P is greater than 0.05, was the null rejected at P is greater than 0.05? The answer is no, right? You'd want P to be, the probability to be less than 0.05 for you to reject the null hypothesis. And that's what we have here. So the homogeneity of variance assumption requires equal population variances, not equal sample variances, although the sample variances should be somewhat similar. And obviously the null is rejected when P is less than 0.05, not when P is greater than 0.05. And that P is the probability of making a type 1 error. So type 1 error is to reject the null when the null is true in the population. So hopefully that sort of introduces the topic. There's a bunch of calculations. You're going to have to go through the calculations yourself, do the practice problems through MindTap. There's practice problems set up in MindTap. You can just do them over and over again. And then there'll be a problem on the exam about independent groups t-test. It's not a very difficult calculation. You just have to be careful when you calculate the pooled variance and make sure you look up the right number in the table. And that's about it. So hopefully that helps a bit. If you have questions, email me or stop by office hours. Bye for now. Good luck with the exam, and I'll talk to you next time.